Good morning, all of you. In previous class, we discussed about basics of recurrence relations, and in last class, we discussed about solution of linear homogeneous recurrence relation. So the working rule for linear homogeneous recurrence relation is first we find degree of the given recurrence relation, and after that we write characteristic equation. So by solving characteristic equation, we get the roots. Here three cases are arise. If the roots are distinct, the solution is C1 R1 power n plus C2 R2 power n plus and so on. And if the roots are real and equal, then the solution is C1 plus C2n plus C3n square plus and so on plus Ckn power k into R power n. If the roots are complex numbers, the solution is R power n into C1 cos n theta plus C2 sin n theta. So these are the cases arising in when finding roots of the characteristic equation. So after finding the solution, we eliminate arbitrary constants using initial conditions. Okay. So already we solved some problems in today class also. We are go with another problem. So the problem is find an explicit formula for the Fibonacci numbers. So the solution. So the Fibonacci numbers are 0, 1, 1, 2, 3, 5, 8, 13. The recurrence relation corresponding to Fibonacci sequence is Fn is equal to Fn minus 1 plus Fn minus 2, n greater than or equal to 2. With the initial conditions, F0 is equal to 0, F1 is equal to 1. Okay. So first we write the characteristic equation of this Fibonacci recurrence relation, and the degree of this recurrence relation is 2. So the characteristic equation of this recurrence relation is r square minus r minus 1 is equal to 0. So we solve this characteristic equation, we get the roots r is equal to 1 plus r minus root 5 by 2. So the general solution is here two different roots. The first root is 1 plus root 5 by 2 and the second root is 1 minus root 5 by 2. So the solution of the recurrence relation is Fn is equal to C1 into R1 power n. So here R1 is 1 plus root 5 by 2 whole power n plus C2 into R2 power n, 1 minus root 5 by 2 whole power n. This is the solution for the 1 minus root 5 by 2 whole power n. Okay. So where C1 and C2 are the arbitrary constants. So we have to find these arbitrary constant using given initial conditions. So we put n is equal to 0 in this relation. So let it be equation 1. So we put n is equal to 0 in equation 1. That equation 1 becomes f naught is equal to c1 1 plus root 5 by 2 whole power 0 plus c2 1 minus root 5 by 2 whole power 0. Okay, anything power 0 value is equal to 1. So here the given condition f naught is equal to 0. So we substitute these values, we get the equation c1 plus c2 is equal to 0. So and we put n is equal to 1 in equation 1, we get the another equation in c1 c2, that is c1 into 1 plus root 5 by 2 plus c2 into 1 minus root 5 by 2, that is equal to 1. So this one is value for f1. Okay. So let it be equation 2 and Let it be equation 3. Solving 2 and 3. From equation 2, we write C1 is equal to minus C2. C1 is equal to minus C2. So substitute this value in equation 3. The total equation is in C2 terms. So from this C2 is equal to minus 1 by root 5. So we substitute this value, we get C1. So C2 is equal to minus 1 by root 5 and C1 is equal to 1 by root 5. C1 is equal to 1 by root 5. So substitute the C1 and C2 values in equation 1. We get the general solution for the Fibonacci recurrence relation. That is Fn is equal to, so C1 value is 1 by root 5. 1 plus root 5 by 2 whole power n minus 1 by root 5 into 1 minus root 5 by 2 whole power n greater than or equal to 0. This is the general solution for the Fibonacci recurrence relation. Okay. So next another problem. Solve the recurrence relation. So the recurrence relation is an is equal to 2an minus 1 minus 2an minus 2. So initial conditions are a0 is equal to 1 and a1 is equal to 2. So this is linear homogeneous equation. Okay. So an minus 2 an minus 1 plus 2 an minus 2 is equal to 0. So the given relation is linear homogeneous recurrence relation. So the given recurrence relation is an minus 2 an minus 1 plus 2 an minus 2 is equal to 0. So the characteristic equation is, so the degree of given equation is 2. So how to find the degree of the given recurrence relation? Difference between greatest subscript and lowest subscript. So here the greatest subscript is n and the lowest subscript is n minus 2. So from that we write a degree of the given recurrence relation. So that is 2. So the characteristic equation of given linear homogeneous recurrence relation is r square minus 2r plus 2 is equal to 0. R square minus 2r plus 2 is equal to 0. So this, solve this characteristic equation, we get the roots. R is equal to 2 plus r minus root 4 minus 8 by 2. Okay. So here r is equal to 1 plus r minus I. The roots of the given the characteristic equation is a complex number. So what is the solution for complex numbers? The solution is 1 plus r minus I is equal to root 2. So when we get so whenever we get the complex number, the solution is r power n into cos n theta plus I sin n theta. So when r is equal to square root of x square plus y square. So here x value is 1 and y value is 1. So 1 plus r minus I. So that is equal to root 2 cos pi by 4 plus r minus sin pi by 4. So the general solution of the recurrence relation is, the general solution of the recurrence relation is here the root r value is root 2. So how to get this root 2? Here the complex number is 1 plus r minus I. So x is equal to 1, y is equal to 1. So r formula, the formula for r is equal to square root of x square plus y square. So r is equal to root 2. So r is equal to root 2. Okay. So we substitute r value and theta is equal to, what is the theta value? Tan inverse y by x or cos n pi by 4 plus or minus c2 sin n pi by 4. So an is equal to root 2 whole power n C1 cos n pi by 4 plus or minus C2 sin n pi by 4. This is the solution of the given equation. So let it be equation 1. Now we eliminate the arbitrary constant C1, C2 using initial conditions. The given initial conditions are A0 is equal to 1 and A1 is equal to 2. So put n is equal to 0 in equation 1. We get the equation. So put n is equal to 0, A0 is equal to root 2 whole power 0, 1. So C1 cos n pi by 4 plus C2 sin n pi by 4. Okay, so C1 plus or minus 0 is equal to 1. So A0 is equal to 1. So we get the equation C1 is equal to 1. So let it be equation 2. So put n is equal to 1 in equation 1. A1 is equal to 2. So 2 is equal to root 2 C1 cos pi by 4 plus C2 sin pi by 4, that is equal to 2. Okay. So pi by 4, cos pi by 4 means 1 by root 2, sin pi by 4 means 1 by root 2. So the value, the equation is C1 plus C2 is equal to 2. So here from equation to C1 is equal to 1, from that C2 is equal to 1. So C1 is equal to 1 and C2 is equal to 1. Substitute these values in equation 1, we get the required solution for given recurrence relation, that is an is equal to root 2 into cos n pi by 4 plus sin n pi by 4. Okay, so here C1 value 1 and C2 value 1. So the solution is an is equal to root 2 cos n pi by 4 plus sin n pi by 4. Okay, so the next topic is solution of non-homogeneous recurrence relation with constant coefficient. So, so the next topic is non-homogeneous recurrence relation with constant coefficients. So a recurrence relation of the form an minus c1 an minus 1 minus c2 an minus 2 minus and so on minus ck an minus k is equal to f of n, where f of n not equal to 0. So this is, let it be equation 1. So the recurrence relation is of the form an minus a c1 an minus 1 minus c2 an minus 2 minus and so on minus ck an minus k is equal to f of n. So f of n not equal to 0. So is called non-homogeneous recurrence relation with a constant coefficient, with a constant coefficient. The complete solution of equation 1 is an is equal to an of h plus an of p. So an of h, here h represents homogeneous equation and p represents particular solution. So the sum of homogeneous solution and particular solution gives the complete solution of non-homogeneous recurrence relation. Okay. So in previous problems, we know how to solve homogeneous, how to get a homogeneous solution. So in this, how to find particular solution. So to find particular solution, so particular solution is denoted by an of p as follows. So f of n, RHS term of the recurrence relation. So RHS term of the recurrence relation form of particular solution. If RHS term of the recurrence relation has constant term, then the particular solution is D. Then the particular solution is D. If the RHS term of the non-homogeneous recurrence relation has linear function, that is C0 plus C1n, then the particular solution is D0 plus D1k. Okay, so if the non-homogeneous equation RHS term is of the form C0 plus C1n plus C2n square, then the particular solution is D0 plus D1k plus D2k square, and so on. If that is nth degree polynomial, then the particular solution is also D0 plus D1k plus D2k square plus and so on plus dmk power m. So in another case, if the RHS term is of the form r power n, comma r, so here r power n and r are real numbers, and means here r value is real number, so like 2 power n, 3 power n, 4 power n. So the RHS term in that, in this form, so the particular solution of that equation is dr power n. Okay, and these are the cases when we solve the particular solution, we get any of these cases. Okay, if our assumption is correct, we get the unknown coefficient from the given equations. So the general solution of the non-homogeneous recurrence relation is the sum of the homogeneous and particular solution. Sum of the homogeneous and particular solutions. Okay. So problems on non-homogeneous equations. Solve the recurrence relation an is equal to 3an minus 1 plus 2 power n with initial condition a naught is equal to 1. With initial condition a naught is equal to 1. So this is a non-homogeneous recurrence relation. So the recurrence relation has RHS term 2 power n, and given initial condition is a naught is equal to 1. So the non-homogeneous recurrence relation is an minus 3an minus 1 is equal to 2 power n. So what is the solution of non-homogeneous equation? An is equal to an of h. H means homogeneous solution plus an of pp means particular solution. So first case we find homogeneous solution, that is the associated homogeneous equation is the RHS term is equal to 0. So an minus 3 an minus 1 is equal to 0. So this is first degree linear homogeneous equation. So the characteristic equation is r minus 3. So from that r is equal to 3. So the root of the equation is r is equal to 3. So the homogeneous solution is an of h is equal to c1 3 power n. c1 3 power n. Okay. So let it be equation 2. So next we find particular solution of the given recurrence relation. So since the RHS of the recurrence relation is, so RHS of the recurrence relation is 2 power n. So here r value is 2. So this is of the form r power n form. In this r value is equal to 2. Okay. So and here in homogeneous equation we get r value 3. So here 2 is not the characteristic root. Let the particular solution of the recurrence relation be. So the RHS term of the given recurrence relation is of the form r power n. When the RHS term is of the form r power n, the particular solution is dr power n. So an is equal to d r power n. So in place of r is equal to 2. It is given d2 power n. So it gives the solution of equation 1. Using this equation in the given recurrence relation, we get, so we substitute these values in equation 1. So in place of an d2 power n, in place of an minus 1, 3d 2 power n minus 1 is equal to 2 power n. Okay. So d 2 power n minus 3d 2 power n by 2. 2 power n by 2. Okay. So 3 by 2 into d is equal to, so in both terms 2 power n will be common and it will be cancelled on left and right and left hand side. So the remaining term is d minus 3 by t d is equal to 1. So this can be written like d 2 power n minus 3 d 2 power n by 2 is equal to 2 power n. In this term 2 power n will be common. So we get 2 power n common and we get in brackets d minus 3 by 2 d is equal to RHS side, right hand side 2 power n. So in both sides 2 power n will be cancelled and remaining d minus 3 by 2 d is equal to 1. So from LCM we take LCM 2d minus 3d, that is equal to 2. So from this we get d is equal to minus 2. So we substitute d value in equation an is equal to d2 power n. So from this is particular solution. So what is the particular solution? An power p is equal to d2 power n. So an power p is equal to d value is minus 2 into 2 power n. So minus 2 whole power 2n plus 1. So let it be equation 3. Hence the general solution of equation 1 is, the general solution of equation 1 is an is equal to an of h plus an of p. So here an of h is equal to c1 3 power n and an of p means particular solution. So particular solution is minus 2 power n plus 1. So now we eliminate arbitrary constant using initial condition. So then we put n is equal to 0 in equation 4. We put n is equal to 0 in equation 4. We get a naught is equal to c1 3 power 0 minus 2 power 0 plus 1 1. So 3 power 0 1. So a naught value is given 1. So 1 is equal to c1 minus 2. So c1 is equal to 3. So substitute c1 value in equation 4. We get required solution for given non-homogeneous recurrence relation, that is an is equal to 3 power n plus 1 minus 2 power n plus 1. So this is the required solution for given non-homogeneous recurrence relation. Okay. So next problem, solve the recurrence relation an is equal to 2an minus 1 plus 2 power n, a naught is equal to 2. So the given recurrence relation is an minus 2an minus 1 is equal to 2 power n. Let it be equation 1 and given initial condition is a naught is equal to 2. First we find homogeneous solution for equation 1. So the homogeneous equation is an minus 2an minus 1 is equal to 0. So the characteristic equation is, this is degree of 1. So the characteristic equation is r minus 2 is equal to 0. From that r is equal to 2. So the homogeneous solution is an of h is equal to c1 2 power n. So c1 2 power n, let it be equation 2. So in case 2 we find particular solution. So for taking particular solution, so RHS term of the given recurrence relation is 2 power n. So here R value is 2 and that value is equal to characteristic root. Okay. So in such type of cases, we consider particular solution. an is equal to dn 2 power n. An is equal to dn 2 power n. When we take this type of solution, when RHS term of the given recurrence relation has R value that is equal to characteristic root, in such type of cases we take the solution n is equal to dn 2 power n. Okay, so using this equation in the given recurrence relation we get dn 2 power n for n minus 1 terms, n minus 1 term minus 2d in place of n minus 1, 2 power n minus 1 is equal to 2 power n. So dn 2 power n minus, so here 2 power n minus 1 d into n minus 1, 2 power n minus 1 is equal to 2 power n. 2 power n will be common. We get n minus 1 is equal to 1. So d is equal to 1. So we substitute d value in this solution. So an power p is equal to d value 1. Remaining is n into 2 power n. So let it be equation 3. So the complete solution of given recurrence relation is an is equal to an of h plus an of p. So an of h is a homogeneous solution and an of p is particular solution. So homogeneous solution is C1 2 power n and particular solution is n 2 power n. So let it be equation 4. Now we eliminate arbitrary constant from this equation using the initial condition. So initial condition is a naught is equal to 2. Okay. So put n is equal to 0 in equation 4. A naught is equal to C1 2 power 0 plus n in 0 into 2 power 0. So C1 is equal to 2. So substitute this value in equation 4. We get the required solution of given non-homogeneous recurrence relation. That is, therefore, the required solution is an 2 into 2 power n plus n into 2 power n. Bases are equal, powers, adding powers are common the terms 2 power n. So an into 2 plus n into 2 power n. An into 2 plus n into 2 power n is the solution. Okay. Next problem. Solve the recurrence relation an minus 2an minus 1 plus an minus 2 is equal to 2. So here RHS term is 2. This is non-homogeneous recurrence relation with initial conditions a0 is equal to 25 and a1 is equal to 16. So first we find homogeneous solution. So the given recurrence relation is of the degree 2. So first we write characteristic equation of given recurrence relation, that is r square minus 2r plus 1 is equal to 0. Solve this characteristic equation, we get r is equal to characteristic roots 1 comma 1. So the homogeneous solution is, here the roots are equal. So the homogeneous solution is a1 of h is equal to c1 plus c2n into 1 power n. So here r value is 1. So case 2. So what is case 2? Particular solution. So since the RHS of the recurrence relation is 2, it is a constant. So RHS term has constant, then the particular solution is D. Okay. An of P. An of P is equal to D. It is also a constant. So using this solution in the given recurrence relation, we get, so an of P is equal to D minus 2D plus D is equal to 2. So total 0 is equal to 2, which is impossible. So thus our assumption is wrong. So now we assume that an of P is equal to nd. Okay. So using this solution in the given recurrence relation, we substitute in place of an, nd, n minus 1, n minus 1 into d, n minus 2, n minus 2 into d is equal to 2. So we solve this equation, which is also LHS not equal to RHS, so which is also impossible. So thus our assumption is wrong. So we take another attempt, that is a KHK is equal to n square d. So using this solution in the given recurrence relation, we get n square d minus 2 into n minus 1 whole square d plus n minus 2 whole square d is equal to 2. Okay. So we solve this equation, we get d is equal to 1. So we put d is equal to 1 in this equation, d is equal to 1. So an of p is equal to n square is the particular solution for given recurrence relation. So hence the general solution is an is equal to an of h plus an of p. So an is equal to, this is the homogeneous solution and this is particular solution, sum of homogeneous solution and particular solution. So now we find C1 and C2 values using initial conditions. So put n is equal to 0 in equation, in this equation. So given a0 is equal to 25 and a1 is equal to 16. So we put n is equal to 0, we get c1 is equal to 25, and we substitute this value, we get c2 is equal to minus 10. So the required solution of given recurrence relation is an is equal to 25 minus 10n into 1 power n plus n square. So an is equal to n square minus 10n plus 25. Okay. Thank you.